Hi, in this video, we want to take a look at the different variance-covariance structures in generalized least squares. All right, so we're going to be using the NLME package in R to achieve this. All right, so remember, if I'm doing regular linear regression, simple linear regression, I have first assumption is the linear model. Second assumption is that the expected value of residuals is 0. Third assumption is that the conditional variance, so of the residuals given the predictors, is constant. And then we have the conditional covariance given X between observations is 0. Okay, so if the constant variance or 0 covariance between our observations fails, then we can't use regular linear regression. What we need to do, we need to do something else. Well, generalized least squares comes to rescue. Oh, something I also want to say, if you also have normally distributed residuals as an assumption, and you have covariances of 0 between the observations, that means that your observations are independent. Okay, so if I believe that I have normally distributed residuals, but I don't see like independence in my plots, then I know that I can't use linear regression. I need to use generalized least squares regression. Okay, so we're gonna run through an example. The example is from a modern approach to regression with R. And I've very much modified this. I want to put more of an emphasis on model building rather than like, what does the model mean? Because, you know, a lot of times when we're building models, we actually don't care about like how we got the model. We care about, is this a good fit? Will this work? Now, the theory behind it frequently is not as important. Now, theory is important because it helps guide us in situations when we don't have enough data. It helps prevent us from making serious mistakes. But my opinion is that first thing we need to master is just being able to do it and then evaluate model quality. And then theory is, I feel, easier to learn when you have a frame of reference. Okay, so first thing we're going to do, we're going to load the data. So this is the Bay Area data set from the textbook that I mentioned. And I'm going to truncate, print it out digits down to 3 significant digits just to keep it from being like overwhelming because human beings are looking at this. All right, so for this example, what we're going to do, we're going to build a linear model. We're going to look at the linear model and go, hey, I don't have 0 covariance, or I don't have independence between my observations. So what we're going to have to do, I'll have to do something else. So let's start looking at the different forms of correlations that we could have between our residuals and then proceed from there. All right, so let's go ahead and look at the scatter plots. And as always, I like to color my points by an important variable, and I'm coloring them by the target variable. For us, the target variable is the interest rate. And so we're just doing the scatter plot matrix, pretty standard. All right, so it looks like there's something going on between interest rate and loans closed. Here, vacancy index, I see kind of like a Z pattern. Now here, I look at loans closed and vacancy index, and I can kind of see like there's a trail going on. Furthermore, since I colored the points by the target variable, I know that like the lighter color ones correspond to a greater interest rate. All right, so I can see that as I go along this trail, we get lower interest rates. So this is something that's nice about coloring the points, is that I can see that there's something going on, and it's going on with all 3 variables simultaneously because of this one plot. Okay. So let's go ahead and build a vanilla regression model. Now, what I'm going to do, I'm going to end up looking at it and going, hey, I have serial correlations. Therefore, I do not have 0 covariance between residuals. Okay, so we're going to build a model. I'm going to say that interest rate depends on loans closed and vacancy index. That's my formula, and I'm throwing in the data set. All right, so I can see that off of the summary statement, it looks like vacancy index is not statistically significant, so I would consider removing it. Here, loans closed is definitely statistically significant. And we have a 0.83 and 0.81 for our R squareds. All right, I'm feeling like there's something going on there. You know, my data, my predictor variables have informative value for the target variable. Okay. So now let's go ahead and plot. Now, when I was building out all of this, I actually applied all 6 of the diagnostic plots. But this first one, the one that R has as the first diagnostic plot, this one is the one that shows that there's a problem the best. So I'm just showing this one because we want to, I just want you to get a feel for how this works, that we build the model, we take a look and go, hey, my assumptions don't hold. What do? I start making adjustments. So I'm going to go through the first diagnostic plot, and I can see that there's a pattern right here. Furthermore, I can see that it's going dark to light on the colors. Well, remember, the larger interest rates were with the lighter colors and the lesser interest rates were with the darker colors. So I can see that the residuals are have this pattern, and the pattern is going along with the target variable. All right, so there's definitely a problem in this. All right, so I know I cannot trust this model. All right, so because of this pattern here that I see that they're kind of like going along this red curve in a way, I think, hey, there might be correlation between the observations. Now, if I was to take a look at the data set, I would see that this is a month-by-month data set. Whenever I see month-by-month data or day-by-day data, week-by-week, hour-by-hour, second-by-second, that kind of data, expect for this to happen. Expect that there will be a correlation between consecutive observations. All right, so I suspect that there is an autocorrelation aspect going on to my residuals. So let's go ahead and take a look at the autocorrelation between my residuals. Here I'm going to use the ACF function. So AC stands for autocorrelation. And I'm going to plot the residuals from my linear model. All right, so remember that in autocorrelation, lag 0 is the correlation between observation and itself. So lag 0 is always going to be 1 no matter what's going on. Now here, this is the correlation between observations and the one before. Here, this is the correlation between observations and the 2 previous. Correlation between observations and the 3 previous, three steps back. All right, so here we can see that we have, you know, a correlation going on. Then it shrinks down and it stays within the blue band. All right, so here I conclude using this plot that I need to worry about a lag 1 autocorrelation. So I need to worry about the correlation between observations and the one prior. Okay, so this tells me immediately that I need to use generalized least squares. All right, so what I'm going to do is I'm going to build generalized least squares. Now, each time I do this, I have to specify the correlation structure. I don't have to be very specific. I just have to say the structure of it. Some like ARMA, you have to be more specific. You have to say, like, you know, what the P and Q are. Well, there's going to be a bunch of these models. What I'm going to do to keep my workspace tidy, to keep it clean, and to keep everything organized, I'm going to put all of my models into a list. I'm going to call it list GLS because I'm using the GLS function to generate the models, and this is the list containing all of them. Okay, so first thing I need to do, I need to get a baseline model. How the NLME package works. It works very efficiently if I have like a baseline model, and then I go in and I update the correlation of that model to make a new model. Or I can go ahead and change the weights. And that's another way to address problems. Okay, so what I'm going to do, my baseline model is just going to be the same formula as my linear regression model. And I'm going to fit by maximum likelihood. And there's other parameters in here, but this is what the author of the textbook chose. do whatever works best for you, whatever you feel most comfortable with. Look at the help documentation and see what your options are. Okay, so the first new model I'm going to get is I'm going to take a look at autoregression with lag 1. So here I'm taking into consideration the correlation between the observations and the previous observation. And we're using a formula that, and we're saying that it depends on month. I'm going to be using the formula where it depends on month every single time. Okay. Now I want to do an autoregressive moving average process with arbitrary orders for the autoregressive and moving average parts. All right, so this arbitrary orders, what this is saying is I'm dictating like the structure of the autoregressive moving average. Remember, there's two parts. There's the autoregression and the moving average. So autoregression is that is a correlation with previous observations. Moving average is exactly what it sounds, that the average is changing over time. It's moving as time goes on. Okay, and P and Q are the parameters for this. And so you'll see, just like in autoregression 1, I set the parameter to correlation AR1. Now, something I need to point out is that I'm using the update function. I'm taking the update function, I'm passing my baseline model, and then I specify what has changed about that model. I'm using the update function, I'm putting in my baseline model, and then I'm saying what has changed on my model. What do I want different? All right, now let's take a look at continuous autoregressive process, AR1 process for a continuous time covariate. A lot of words in there. So here, when I use the update function, I use core car1. So this is continuous autoregression. So correlation, continuous autoregression, lag 1. Then I want to look at compound symmetry structure corresponding to a constant correlation. So I'm using correlation and comp sim. Now, next one is exponential spatial correlation. Now, if you've taken a time series course, these terms are very familiar to you. If you haven't, well, just know that these are, very common models in time series. For us at this point, we're not worrying about what these really mean or what the models are. We're just worried about, does this fit my data very well? If it looks like I have a good model, that's, a lot of times all we care about. What we can do, we can fit a model, see that it looks good, then figure out what the structure really is. And then we can talk about it and report it to the decision makers. All right, so here's the exponential spatial correlation is core EXP. Now we have Gaussian spatial correlation, so correlation Gaussian. Linear spatial correlation, yeah, it's correlin. Now I'm doing these in order of the name of the correlation function. That's the order that I chose them in. This is not related to the structure at all, at least the order that I put them in. Now rational quadratic spatial correlation, so core ratio is rational quadratics. Then we have spherical spatial correlation, that's core sphere. General correlation matrix with no additional structure is core sim. All right, so now I've got a bunch of models. I've got them all on the one list. So now what I want to do, I want to take a look and I want to see which one looks like the best. Are there multiple that look pretty good? Do I have like a bunch of competitors? How does my baseline model compare to the others? Let's find out. Okay, so what I'm going to do, I want to extract the features of the models. And specifically, I'm going to look at the log likelihood, the Bayesian information criterion, and the Akaike's information criterion. Okay, so what I'm going to do, when I apply the summary function to a GLS object in R, there are 3 things that are included in the summary. Now, there's a whole bunch of stuff that gets spit out, but here we're going to focus on 3. We're going to focus on the log likelihood, Bayesian information criterion, and the Akaike's information criterion. Why? Because those give me an evaluation of model quality. All right, well, what I want to do, I like to look at my models like ordered, like, you know, worst to best, best to worst, something like that, just so I can get a feel what's going on. So what I'm going to do, I'm going to extract the log likelihood. So notice I've created this function. This function, I pass the GLS object into summary, and then I grab only the log likelihood. Now, sapply, what it does, it applies this function with a parameter of fun, isn't that fun? Haha, to every object in that list. Okay, so now that I have all the log likelihoods, I'm going to sort my list by the order of V. That way I can go from worst to best by the log likelihood measurement. So now I've got it sorted. So my list if I was to look at my list at this point, I would see that like the first model that's in that list is going to be the one with the lowest log likelihood, and the last one is going to have the greatest log likelihood. So now let's go ahead and extract the 3 model quality measurements that come out that I'm interested in. And I'm going to put this into a data frame. So I use a transpose function to convert the format of the output to the way I like it. And then I'm going to go ahead and set it up so that my, excuse me, the model names are an ordered factor in order of the log likelihood is what I do here. And this just cleans up some formatting problems that I had with the output. All right, so let's look at the actual values. All right, so when I look at this, I can see that for core sim, the log likelihood was 11.6, which is the same as my baseline. Then we get our Gaussian, rational, exponential, continuous, autoregressive, autoregressive 1, autoregressive moving average, core spherical, core lin, and so on. All right, so I can see that here, this is my best model by these 3 statistics. You'll notice that this increases as I go down, and this decreases as I go down also. This shows me that these 3 values are very consistent with each other. Now, it's not a continuous step difference between them, which is all right. Oh, now something I would want to consider. Let's say for some reason I was gonna use one of these 2 models, either baseline with no special correlation structure, or the core sim. Well, I want, if the statistics were the same and I've got 2 competing models, I want the simpler one. So I would go with GLS 0, which is the default setting. Now, if I was considering to use one of these 3 models, I would go with autoregressive 1, because this is simpler than continuous autoregressive, and this is simple, and which both of these is simpler than the exponential smoothing. But overall, I would pick this one. All right, so now let's go ahead and plot these. Let's go ahead and see, is there a big difference? How do we feel about the comparison of these? So I chose to use ggplot to do this, to get the bar plots. So I can see vertically, it gives me the log likelihood, and as it goes up. All right, so we can see that these 2, there's not much of a difference, but this one is the better model by this criterion. But all of these are pretty close. So if I needed to go with a simpler model, I would probably go with autoregression 1. But all of these are pretty tight competitors with each other. So I would want to consider what's my audience willing to accept? Do I feel like I would have overfitting with all the different parameter estimates on variance covariance if I was to use one of these models over here? So these are things you always have to balance. Think about it. Think about the structure of your model, and is it worth it to have the additional parameters, the additional complexity? All right, well, I can go down and I can go with the Bayesian information criterion. Remember, more negative is better when we talk about Bayesian information criterion. So something that's interesting is that, so remember, I've got everything ordered by log likelihood. So it matches pretty well with the Bayesian information criterion, but I can see that things actually get worse when I go from autoregression 1 to autoregression moving average. So here, this is autoregression 1. This is an autoregression 1 moving average 1 model. That additional moving average model, the moving average aspect, by BIC's measurement, is not worth it in comparison to autoregression 1. Now let's look at Akaiki's information criterion, and I see the same result. So for me, I would go with one of 3 models if I was going to be doing this at work. If I needed a very simple model, and so that's all, it's not unlikely that I would be in the situation where I have to just do a simpler model that I'm comfortable with. That I have to get people to believe my model. If the people who are receiving my model and are going to be basing decisions off of them, if they don't feel comfortable with the model they don't understand, my models are useless. So it's better to go with a simpler model that decision makers trust than the most advanced, slickest model ever that doesn't get used. All right, so if I needed a model that they could trust, that like somebody with a weak math background would be likely to accept, I would go with the default model. Well, this is going to be equivalent to regular linear regression. So something to think about. Now, if I'm in a situation where I just want the best model possible and I don't care how I got it, then I would go with this one over here, the core comp symmetric. Now, if I wanted a balance between complexity and fit, for me, I would be going with autoregression 1. I have to consider your audience, consider the situation you're in. All right, so now let's go ahead and do an ANOVA test. Let's see if our best model by log likelihood, BIC and AIC, is it statistically more informative than our baseline model? All right, well, I just go ahead and pass both models. Remember, they're in lists, so I have them in this format. I just pass both models to ANOVA at the same time. And you'll notice that it prints out the AIC, BIC, log likelihood, tells me the degrees of freedom, which is nice. So here we can see that I only have one more parameter that I'm estimating. That's something to think about. And we can see here's our likelihood ratio, and our p-value is within machine accuracy of 0. Therefore, I conclude that the core comp symmetric model is statistically significantly different, more informative than the default model. All right, that's all I've got for you. Take care and goodbye.